Today we are going to do LS and JJ coupling under atomic and molecular physics. This is the part 1. So in part 1 we'll basically see the important results from LS coupling and JJ coupling, and in part 2 we'll do problems. So what we are going to do is we are going to just briefly go through the results of LS and JJ coupling. So LS coupling, so when do we have LS coupling? LS coupling we have in light atoms, and the most dominant interaction in an atom is the Coulomb interaction. After that it depends. So in LS coupling what happens is that in LS coupling you have the spins. Let's change the color today. So in LS coupling what happens, the spins combine separately. So we have, if many electrons, the spins combine separately, and then the orbital angular momenta combine separately, and then these two combine to give the total angular momentum. That is the scheme of LS coupling. And after Coulomb interaction, the most dominant interaction in LS coupling that contributes to LS coupling is the spin-spin correlation. Because of spin-spin correlation we have this LS coupling scheme. Let us see an example of this. Before that, LS coupling is governed by what is called the Hund's rule, and we'll just see what's the Hund's rule is. The Hund's rule is the Hund's rule for less than half-fill orbital. We'll do an example to understand this. So what is the rule? Higher value of S is the spin quantum number, is the total spin quantum number. The higher value of S implies lower energy. Okay, and higher value of L implies lower energy, and then lower the value of J, lower is the energy. So this will be the most dominating. This will be the most dominating. Then comes this, and after that comes this. So this is for half-fill orbital. So let us consider the example of two electrons. One electron is in 4s state and other is in 3d state, and this is the non-equivalent because here the principal quantum number 4 and 3 they are different, then S and D are different, so it's a non-equivalent case. So one electron is having the spin quantum number half, and the other electron is also having spin quantum number half. So the total spin quantum number S varies between, it can have values 0 and 1. Okay, so the S have combined spin of one electron and the spin of the second electron, they have combined to give total spin quantum number 0 and 1. Now we go to L1 is equal to 0. So this is the orbital angular momentum of the electron in S is equal to 0. So this is L1 is equal to 0, and in D L2 is 2. So what are the, so L1 and L2 combine, so this orbital angular momentum combine to give, here we can have only one value, and that is L is equal to 2. So now we can combine. So we have L is equal to 2 and S is equal to 0. So this gives the energy level given by the spectroscopic notation D. This is the multiplicity 2s plus 1, and this gives me the total angular momentum, which is here 2. because here it's 2 plus 1, 2 plus 0, J can only take the value 2. And here we have L is equal to 2 and S is equal to 1. So J can take the values 2 plus 1 to 2 minus 1. So it can take the values 1, 2 and 3. Since L is equal to 2, in the spectroscopic notation D, we have D. So this is we have D here, D and D. S is equal to 1 means multiplicity is 3 and J is equal to 1, 2 and 3. So if we see the energy level, so the main splitting is because of spin-spin correlation. So S is equal to 1 and this is S equal to, this is the main splitting, and we know from Hund's rule, we know that higher the value of S, lower will be the energy. So S is equal to 1 corresponds to low energy. And now you can see all these are D, so they have orbital angular momentum same, but the J values are different. And you can see J is equal to 1, J is equal to 2 and J is equal to 3. So as we saw in Hund's rule, lower the value of J implies lower energy. So this is the lowest state, this is the ground state. After that, this is the first excited state. So it is like this. So this is the 4s 3d splitting because of LS coupling. Now we go to an interesting case of what we call equivalent electrons. So equivalent electrons, NP2. So why do we call them equivalent electrons? So here we have 2 electrons in the p orbital and the quantum number is same. Quantum number is same and both the electrons have orbital quantum number same. That is L is equal to 1. So in these cases, when we employ the LS coupling scheme, we have to be careful. So we'll do this NP2 case. So NP2 case means here P means one electron having orbital quantum number 1 and other one is also having orbital quantum number 1. Then the composite quantum number, orbital quantum number, can take the values 0, 1 and 2. Again S1 is equal to half and S2 is equal to half. So the S quantum number can take the values 0, half plus half and half minus half and half plus half, which is 1. Now we have to be careful here because we have to satisfy Pauli's Pauli's exclusion principle. That is, all quantum numbers, if we have 2 electrons, they cannot have all their quantum numbers cannot be identical. Somewhere they have to be different. So in this case, we already have this n quantum number identical, then p identical. So now we have to be careful and see what are the possible cases. So we have S is equal to 1. So this we are taking. So we have S equal to 0 and S equal to 1. If S is equal to 1, then we can see that the possible values, Z component possible values are -1, 0 and 1. So in this case, it's possible that MS1 and MS2 are identical. Okay, so it can be that MS1 is half and MS2 is half. So if S is equal to 1, MS1 is equal to MS2. Sorry. ms1 is equal to ms2 is a possibility. And since this is a possibility, now we have to, so these two quantum numbers can be same. So we have to make sure that the quantum number corresponding to this ml1 and ml2, they should not be same. If ml1 and ml2 can also be identical, then that's not a possibility. So if L is equal to 1, we can see then this condition is satisfied. Why? Because L is equal to 1 means so possible values of L will be z component minus 1, 0, minus 1, 0 and plus 1 and plus 1. So that means you can have minus 1 when say one electron is up and the other electron. So one electron, so the orbital, the z component of one electron is say minus 1 and the other one is 0. So like that we can see that this is a possibility, and this does not have, so this will always be true, that ml1 will not be equal to ml2, because if ml1 is equal to ml2, that means the two electrons can both have this value 1 and 1, then in that case it will become 2. So 2 is not a possibility for z component when L is equal to 1. So like that you can satisfy yourself that for L is equal to 1, ml1 is not equal to ml2. Like 0 you can obtain when one electron is in having z component plus 1 and the other one is having z component minus 1. But for L is equal to 0 and 2, so S is equal to 1, but for L is equal to 0 and 2, you can see that ml1 can be equal to ml2. That's possible. And see if this is possible, then like for L is equal to 0, then both the z component of the orbit, the orbital z component will be 0. Okay, so there is, in this case for L is equal to 2, it's possible that the orbital z component of both the electrons is plus 1 and plus 1 or minus 1 and minus 1. So ml1 is equal to ml2 is a possibility, and since it's a possibility, this when S is equal to 1, L is equal to 0 and 2 cannot happen. So when S is equal to 1, we can only have L is equal to 1. Okay. So if that is the case, then J can take the values 1 plus 1 to 1 minus 1. So when S is equal to 1 and L is equal to 1, then J can take the values 0, 1 and 2. Okay. So when S is equal to 0, that is the spin is 0, so that implies that both the electrons are not in the same quantum state. The spin component, the z component of the spin, if one is plus half, the other is minus half. So in that case there is no restriction, we can easily include L is equal to 0 and 2. Okay, and if we include L is equal to 0 and 2, so L is equal to 0 is not a problem, and we will see that L is equal to 1 is not possible in this case, we can see. So if L is 0 and 2, the possible values of J will be 0 and 2. That is it. So now we can write down the states in spectroscopic notation. So this is my P2. So again, so we have two S. One is S equal to 0 and one is S equal to 1. S equal to 1 is the lower energy. So this is the principal splitting that is taking place because of spin-spin correlation. And then this splitting is taking place because of interaction between orbital angular momentum, because of interaction between S and V. Okay, so here we have 1s0 and 1. So 1 comes from 2s plus 1. Okay, so S is equal to 0. We can see if S is equal to 0, S is equal to 0, J can have only values 0 and 2. 0 and 2. So here S, and then another value of orbital angular momentum will be d. And when S is equal to 1, we have seen the possible values of J are 0, 1 and 2. So 0, 1 and 2. And you can see here the angular momentum, this orbital angular momentum here is P, that is L is equal to 1. So the lowest will be one with having the lowest J according to Hund's rule, because this is less than half filled. So this is less than half filled. So we will be, so we have to, so this is less than half filled. So we will be following this one. This is the Hund's rule that we will be following. Okay, so this is the P2 splitting, and then we have the Hund's rule for more than half filled orbital. That is, here what is the rule? Higher value of S implies lower energy, same as before, lower energy. Then higher value of L, that is orbital angular momentum, implies lower energy. And then we have higher value of J implies lower energy. So this is where it is different. This is the one that is different here. Okay, so this is the one that is different here. And in the previous case it was lower the value of J, lower the energy. Here it is higher the value of J, lower the energy. So we will do an example here. So that we will do the NP4. So here what we are doing is so now we have 4 electrons, 4 equivalent electrons here. So principal quantum number is the same, n, and for each electron the orbital quantum number is L is equal to 1. So what will be the splitting of energy due to Ls? So actually this is an easy problem if you just have to take note of one thing. So number of holes in this problem will be, so in P orbital you can have maximum 6 electrons. Here we have 4 electrons. So we will say we have 2 holes. Hole means positively charged electron. So what we have is this. So this case is very similar to this NP2 case, but there is a crucial difference. What is the difference? Here the p orbital is more than half filled. Here the p orbital is more than half filled. So half filled will be 3. Here we have 4 electrons. So it is more than half filled. So the energy levels here will be identical, but their arrangement will be different. So here is the P4. Okay, so this is the principal splitting. This is identical. S is equal to 0, S is equal to 1. Then we have 1s0 and 1d2. Well, this is this, and here, and so this will be actually, this is wrong. So this one will be actually your this is this is correct. This is correct. So this is 1s, so this is 1 s0 and this is 1d2. So this is interaction between the orbital angular momentum. It's fine. So here you can see, here it is different, because here the p's are different, so the difference in energy is due to the different total angular momentum. And for Hund's rule, in this case, we know this: higher the value of J, lower the energy. So here it will be 3p2 will be the ground state, then we have 3p1, and then we have 3p0. It is like that, and that is where it differs from this p2 case. Next, we can advance it further. We can go to n-d2 electrons. This is also equivalent case. Principal quantum number is same, and the orbital quantum number will be L is equal to 2 for the 2 electrons. Here also we have to be careful not to violate Pauli's exclusion principle, and you have to, this case is very similar to np2 electrons, but we will not do in details here. So if you do the calculations, then this d2 will be split into, again this is the major splitting, s is equal to 0 and s is equal to 1, and then s is equal to 0 will be split into 1s0, this is spectroscopic notation, 1d2 and 1c4. Okay, here also this is the, here it is then divided into this p and f state. So p is the orbital quantum number, L is equal to 1. Here it is S, D, and this is G. This is G actually, G4. And this is F. So this is F. This is 3P-F4, 3F3, and 3F2. Okay, so this is how, if we consider two equivalent D2 electrons, then this LS coupling scheme is like this: S equal to 0, S equal to 1, then the splitting occurs due to spin orbit, due to your coupling between the orbital angular momentum. Here the orbital angular momenta are the same, p, p, p. So this is basically LS coupling that determines this splitting. This splitting is determined by all this LS coupling. Okay, here also it is F. So the orbital angular momenta are the same, and the splitting is determined by LS coupling. Because, so you have so this is also, all this thing is determined by LS coupling. That is for different, so J's are different here. Here 4, 3, 2. That is how the energy level is arranged. And with 2, this is the lowest energy. Okay, and here you can see F, for F the L value is greater, so this is lower than F. So this multiplet is at a higher energy level than this multiplet, which is governed by F, because L value is higher. We are following the Hund's rule here. And now we go to Landé interval rule. So Landé interval rule is, it gives the energy difference between two consecutive multiplets with spectroscopic notation this. So this is the multiplicity Y is the orbital quantum number and J and J plus 1 are the total quantum number. So this difference is due to the LS coupling, because J and J plus 1 are different, otherwise other things are same here. And if you calculate it, then we can find EJ plus 1 minus EJ is actually A times is a constant times J plus 1, A being some constant. So this is the Landé interval rule. So we now come to JJ coupling. So in JJ coupling, what will happen is the orbital and the spin angular momentum of an electron combine to give a net angular momentum. This net angular momentum of the electron then combines with angular momenta of other electrons to give the total angular momentum. And in this case, the dominant interaction is not spin-spin correlation. The dominant interaction is the spin-orbit coupling. That is why this orbital and spin, they interact with each other. And this causes the main splitting of the energy. So let us see JJ coupling for two electrons. One is 4p electron and 4d electron. So for p electron, L1 is 1 and S1 is half. And for d electron, L2 is 2 and S2 is half. So LS coupling, so this L and S1, they can combine to form J1, and the possible values of J1 are 3 by 2 and half. And from this L2 and S2, we get J2 is equal to 5 by 2 and 3 by 2. So now J1 and J2, so this is this combination J1 J2 gives me these combinations, 3 by 2 and this 5 by 2, 3 by 2 and this 3 by 2, then half 5 by 2, and then half and half, half and 3 by 2. So these are the four main splittings we are getting here. And then so this is J1 J2. Now they will come, J1 and J2 will combine to give the total angular momentum. So 3 by 2 and 5 by 2, so what are the possible angular momentum they give? 5 by 2 plus 3 by 2 to 5 by 2 to minus 3 by 2. So that will give us 1, 2, 3, 4. This is the total angular momentum quantum number. For 3 by 2 and 3 by 2, you can easily check. You will get the total angular momentum quantum number 0, 1, 2 and 3. For half and 5 by 2, we get the quantum numbers, total angular quantum numbers 2 and 3, and for half 3 by 2, we get half and 2. So these are this is the main energy level, 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 and in that energy level, these are like multiplets. Okay, so these are the multiplets. The 4, 4, here you have 2, here you have 2. So today we are going to do one problem, and in the part 2 we will do some more problems. So here in this problem, show that the total angular momentum quantum number, that is J, changes by 4 when chromium has a valence electronic configuration of 3d6, okay, makes a transition from its ground state to its ionic form Cr2 3t4. So from one ground state, make a transition from its ground state to the ground state of its ionic form. So it makes a transition from one ground state to another. So what we have to find out, by how much does this total angular momentum change in this transition. So for D6, the ground state is always determined by maximum S and maximum J. That is Hund's rule. Because here the 3D6, the orbital is more than half filled. So here the ground state will be determined by maximum S as well as it will be determined by maximum J and maximum L also. So in this case, so you can see there are so if D6 means like this, so you have, this is the d orbital, so there will be 2 electrons will always be paired. So we have 4 unpaired electrons. So so maximum value of S will be half plus half plus half plus half, that is 4 into half, that is 2. So the paired electron we will not consider, and then we will say the total orbital angular momentum L is equal to 2. Why? That you can easily check. So this is my D6 case. So this can be this box. So here for d orbital, the possible z values are -2, -1, 0, +1 and +2. So and the electrons are situated in these boxes. So one box we have paired electrons. So what about this? So in this case, what we find is we have total z component of the angular momentum is, in this case, 2. That you can easily see, -1 and +1 cancel out and we have 2. So in this case I have placed the paired electron in this box. So ml turns out to be 1. In this case I have put the paired electron in this box. So ml turns out to be 0. Here the paired electron in this box, and ml turns out to be -1 because -2 and +2 cancels out, 0 is there, so we have only -1. And in this case the paired electron is in this box, ml is equal to -2. So these are the possible values of the z component of the orbital angular momentum. That implies L is equal to 2 and there can be no other value. So S is equal to 2 and L is equal to 2. So maximum value, since it is more than half filled, maximum value J will be 2 plus 2, which is 4. Now we go to this case, D is equal to 3D4. So in 3D4, the ground state is determined by maximum S, maximum L and minimum J. Okay, so maximum S is like before, it will be, we have 4 electrons, so it will be half plus half plus half plus half, that is 4 into half, that is 2. What about L? L also in this case is 2. Why? So you can place the electrons like this. So in this case the z component of ml is -2. Okay, you can check easily by adding. If I place the electrons like this, then the z component will be 2. If I place the electrons like this, z component will be 1. If I place the electrons like this one is vacant, then -1, and for this one is vacant, 0. So you can see the possible values of ml vary from -2, -1, 0, +1 and +2. So L is equal to 2. So in this case also L is equal to 2. Now what is the minimum J? Minimum J is L minus S, and that is 2 minus 2 is 0. So the change in the total angular momentum quantum number will be 4 in this case. So today we will stop here, and in the next part 2 we are going to do a few more problems from LS coupling. And thank you.